Hello everyone. Thank you for watching my educational talk on this year ESSCIRC ESSDERC conference. I'm Hadi Heidari from James Watt School of Engineering, University of Glasgow in United Kingdom. Today, I will talk about the principle of magnetic sensing in medical microsystems. In this educational lecture, after an introduction and history of magnetic sensors, you will learn about the principle of magnetic sensors from physics to engineering and how they can be employed for medical applications. We will review different types of the magnetic sensors, including CMOS Hall effect sensors, tunneling magnetoresistive sensors, point-of-care diagnostics using NMR, CMOS-based NMR sensors, and then we will review and see about the handheld tunneling magnetoresistive sensors for malaria hemozoin detections and also for the eye movement gesture control. And at the end, we will conclude and look at the future directions for magnetic sensors. Before starting, I would like to say a few words about where I am from. I'm from University of Glasgow, founded in 1451, is the fourth oldest university in the English-speaking world. It is in the top 1% of the world universities and has several notable alumni, including Adam Smith, Lord Kelvin, James Watt, and several Nobel Prize winners. We have access to James Watt Nanofabrication Center, which includes a 1,400 square meter clean room run as a pseudo-industrial operations and large number of process modules, micro and nanofabrications in different technology, and has a commercial access to Kelvin Nanotechnology company. So is the second highest cited EEE department in the UK, and you can see more information through the links that provided here. So today I would like to discuss just back to the basis. An electronic includes electron, of course. So that electron has a charge and it has a spin. So it's often referred to that an electron, a charged object, has an angular momentum just like a mechanical object that can be rotated in a clockwise or an anti-clockwise directions, as an electrode has so-called spin or a spin angular momentum. This quantity, which is the quantum mechanical, is quantized, so it can only take a value of electron. So it includes a electron charge, which can be named as electronics, or it can be as a spin, which has a which is actually famous for the spintronic. So it's a motion by acting on the spin. So such exploiting of the spin of the electron can be used in different devices for such as the magnetoresistors, a spin transfer torque, a spin hall, and other different devices. So one clear example is the hard disk devices that we have been used in the memory or your computer. So this is a one obvious examples. However, in this lecture today, we will focus on the sensors, and we want to see what is the magnetic sensors and where it comes from and how it works, of course. So first, let's start from anisotropic magnetoresistance. So what is that? William Thomson or Lord Kelvin in 1857 discovered that I found that iron, when subjected to a magnetic force, require an increase of resistance to the conduction of electricity along and a diminution of the resistance to the conduction of electricity across the lines of magnetization. So which this was published in the Proceedings of Royal Society of London. So this was the start of the magnetoresistance that now we call it as an anisotropic magnetoresistance. So anisotropic magnetoresistance, or AMR, has a variation of 2 to 5% at room temperature. So AMR can be detected on the metals, for example, which can have an AMR effect of 2 to 5%. And interestingly, Lord Kelvin comes from University of Glasgow, where I am from. So after Lord Kelvin, till 1988 and afterward, around that, Peter Gromberg and Albert Firth got their Nobel Prize because of their invention based on the giant magnetoresistance, which called GMR. So that is, it says a very weak magnetic change give rise to major differences in resistance in a GMR system. And GMR has made possible miniaturizing hard disk so radically in recent years. In 1997, for example, the first GMR readout head was launched. So indeed, GMR made a revolution in the hard disk industry. GMR has led to a spintronic use of the spin-off electronic to transfer or store informations, and it is considered one of the first real applications of the nanotechnology. So we had a GMR effect, which large increase of the conductance with a structure alternating from magnetic over non-magnetic layer. After GMR, we had a tunneling magnetoresistance. So the obvious difference with the GMR, I'm just explain more in the next slide, is their structure. So their structure in GMR, we are using a conductance layer between the our two layer, our free layer and rotating layer, actually. However, in the tunneling magnetoresistance, Miyazaki and Mudera, interestingly, both of them in 1995, in the two different places, they discovered the tunneling magnetoresistance. However, as you can see, that there is another paper in 1975 from the Julia that we don't know actually who was from, and they actually suggested tunneling magnetoresistance around 20 years before that. So the barrier between the two layers of our sensors, indeed, unlike GMR, which was the conductant layer, we have a barrier which is the isolant and is an isolator, like for example Modera suggested aluminum oxide, which can actually give us a rise of the, as you can see here, it is a delta R over R percentage, and with that around the 10%, or it was till 2008 that magnesium oxide was suggested, and it gives more than 600 percentage at the room temperature. So this was the start of using magnetoresistive tunneling magnetoresistive sensor, in particular using the magnesium oxide. So today we want to discuss about this different type of the sensors. So we will have a look at the Hall effect sensors, which are widely used in the industry, such as automotive. We will explain also about the AMR sensors, anisotropic, GMR sensors, and in particular today we will discuss about the tunneling magnetoresistive sensors. So the physics of them we will explain. So just for your information, we should just say here shows the output and versus the angle of the actually this kind of sensors for the three different magnetoresistors. So they are providing, each of them, they are providing the signal output of the TMR sensors. You can see about 75 times larger than AMR, where GMR is around the where the GMR sensors again providing 23 times less than TMR. So that's why TMR sensors is the our target for the different type of applications. However, it associated with the many challenges such as noise, such as miniaturizations, and how we can control the power for such sensors, which in this lecture we will explain how we can integrate it with the mature technology like a modern CMOS for controlling and cancelling the noise in such sensors. So about the whole aim of this lecture is we want to explain why magnetic sensors needs to be miniaturized. Magnetic systems in medical applications have been used widely for nuclear magnetic resonance, for the magnetoencephalography, for MRI, for the different applications. However, we aim in the future, one of the future directions is to miniaturize them to be used as a portable or wearable or implantable devices. So this can, for example, with having a portable medical diagnostics or biomedical imaging can create it through the integration of the miniaturized magnetic based sensors in biochip platform. So this can reduce the cost. This can give access to the large number of people around the world. It's not only the hospital base, and of course can make a very high spatial resolutions human machine interfaces that we will speak about in the next slides. We can categorize the challenges in three domains. First, for amplifying the low magnetic field. Second is the power management. And third is the noise control and cancellations. We have a different noise associated with magnetic sensors, including the thermal noise, flicker noise, Earth's magnetic noise, Earth's magnetic field, as well as a movement artifact or motion artifact, which is in a just a specific application like implantable or wearables that we have a movement. However, relying on current technology alone is not a long-term solution. The reason is most of the developed sensors are only work on the sensor part. For example, for amplifications, having the signal to noise, higher signal to noise ratio, and other CMOS based sensors, they are not pay attention to the device wise. So that's why we need to have a balance between the both circuit and sensor device. So the aim for us is to detect sub-picotesla magnetic field, which is the picotesla where we are explaining is the range of the magnetic biosignals. If we look at the figure, we have a magnetic sensors, and also we need a CMOS circuitry as a for the processing. So the CMOS circuitry typically is for power communications, for amplifying, for the filtering and cancelling the noises. Our solution should be an integrated sensors which includes the sensor device and readout circuit on the same substrate. So in that case, we can have an effective and high sensitive sensors. Just for examples, over past years, in our group, we have developed different type of the magnetic sensors on chip. So that include the Hall sensors, tunneling magnetoresistive sensors, GMR sensors, and NMR, nuclear magnetic resonance. So our aim was for two main applications. One, human-machine interfaces, and the second, lab-on-chip point-of-care diagnostics. In today's presentations, I would like to give some examples of these devices that we have used for different applications. So we will start from CMOS Hall effect sensors. So CMOS sensors are low cost, very widely used in different applications. So in this work, we can implement the sensors in the CMOS, in the very in a standard CMOS technology. So this work, we have used two sensing device that was a twin for using as a sensing the sensing the output of the sensors was read out by a chopper amplifier, which we used a current spinning techniques for cancelling the flicker noise. So the final chip was fabricated in a 0.18 micrometer CMOS technology, and the sensors could able to detect magnetic field in the range of few hundred nanotons. Value is not enough for very accurate and high resolution biosensors. So in that regard, we have been working on the tunneling magnetoresistive sensors, which are based on the magnetic tunnel junctions. In fact, So if we look at the figure here, so we have a 3 layers, and we have a 1 layer which is the first layer shows a pin layer, and on the top layer we have a free layer which will change. In fact, we can see that based on the parallel or anti-parallel direction of the free layer and pin layer, so we will have a higher resistance when they are anti-parallel direction. However, in the parallel direction we have a lower resistance. So that's why by recording and measuring the anti-parallel and parallel resistance, so when we have a spacer between these 2 layers, we can measure the magnetic field. Okay, let's look at the importance of the magnetoresistive devices. In this section, actually in this figure, what we can play with magnetic sensors, in particular tunneling magnetic sensors. So here shows the publication roadmap of the magnetoresistive sensors. In fact, magnetoresistive sensors, as you can see in the figure, it is expected, while started from 1970s, so it is expected to increase largely in 2030 by applications such as the MEG for the magnetoencephalography or for molecular diagnostics. So they have a different industrial publications. However, as you can see, the future in the next decades will focus on the medical, and in particular bringing such sensors for the medical applications because of working principle of such sensors at room temperature. Our research vision is to create the next generation of magnetic systems that are smaller and less expensive compared to the current technologies, which can be portable and implantable, as well as wearable. Here, the graph shows the magnetic biosignals. So on the right side, on the y-axis, we can see the magnetic flux density, which, for example, for heart or for muscle or brain, nerve here, they are sub-picotesla. And you can see here, while for example, other applications, they are, much, for example, for non-medical, in the industry, they are in range of the microtesla or nanotesla. So just imagine that Earth's magnetic field is around 50 microtesla. So in that case, we can see that our sensors should detect only few picotesla. Different type of sensors that we have been used, it was magnetoresistance, TMR sensors. So currently there are existing optically pumped magnetometers. So there is a group from Nottingham. They are working on the OPM sensors for the wearable MEG, magnetoencephalography. So the sensors manufactured by a Q-spin company. And then we have a flux gate and giant magnetoimpedance sensors, which are they can theoretically they can detect. However, the big problem for such sensors are canceling and controlling the noise at the first time, as well as amplifying and improving the signal to noise ratio. So, as one example in for the first example in this lecture, we want to go and discuss about our research on muscle detection. So we will, which calls magnetomyography. Magnetomyography is the recording and measuring the magnetic field from muscles. So the technology, the first time have been studied 40 years ago. However, 40 years ago, this field was stopped because of the two main challenges. So when the first was because of the detection of the magnetic field was performed by superconducting devices, SQUID, so which are too bulky and expensive. And the second thing was related to the controlling the noise, which was not able to do that one. So our research is mainly to developing tunneling magnetoresistive sensors and magnetoelectric sensors, these two type of sensors for the wearable and implantable magnetomyography. The success in this project can have a huge impact on the diagnosis of different diseases like movement disorders, as well as can be used for the future human-machine interfaces. Next slide, where, as I said, using the SQUIDs in 1972 was explored, and there was another group, our collaborator in a children hospital in Switzerland. They are working on the OPM sensors for the detection of the magnetomyography. However, our group, since past few years, we are working on the integrating the spintronic magnetoresistive sensors and with the CMOS interface for the detection of the picotesla magnetic field from muscles. So we believe that overcoming the challenges related to noise cancelling and as well as the amplifications, we can achieve a wearable and implantable devices for the aim. So maybe I should say a few words about what is the benefit of the magnetomyography compared to the current electromyography. So EMG or electromyography has been used for around 100 years for the measurement and diagnosis of the muscle movements. However, such sensors, they are suffering from the low spatial resolution. So these low spatial resolutions force the technology to be used as a surface or even implantables. So in the hospital, we can see there are neuromuscular implantable sensors that associated with very high risk of the damaging the muscle and also risk of infection. However, our sensors, which is the magnetic base, they don't have any electrical content, so they are less invasive, or let's say minimally invasive, and they cannot, they will not damage the muscle. So on the figure over right, we can see the integration of the tunneling magnetic sensors, which are the, as you can see again, it uses the less than 1 nanometer magnesium oxide barrier between the two free and reference layer over a antiferromagnetic. So this can be integrated with the CMOS technology, which is gives a huge benefit of having a very close readout by integration the spintronic CMOS technology. So in this figure we can see the sensors, how the configurations will be in a Wheatstone bridge, and each sensors will gives a full bridge circuit, and considering the 4 MTJ magnetic tunnel junctions. So the figure here shows the magnesium oxide barrier or spacers, and which is the less than 1 nanometers. And in this work we have the sensors includes more than 1100 magnetic tunnel junction. This figure shows the modeling and simulation results. So as you can see that in a muscle fiber bundle, it depends on the place of the fiber, a single fiber, we could detect the magnetic field generated by each muscle fiber. So here, for example, shows simulations where the biomagnetic field was generated around a single muscle fiber. So the action potential, as you can see, shows here with the magnetic field in the range of picotesla, depends on the places that in the center or on the surface of the signal of the muscle fibers. So here also shows the magnetic field that which is in the range of the nanotesla, that shows the validation and the concept it is working. So in the shows our characteristics and our experimental work, that the work was performed in a shield, actually in a cylinder shield, was that the magnetic earth field was cancelled also by help of the one enhancer, which is the active magnetic cancellation box. And as you can see here, this shows the resistance. For example, we had a Wheatstone bridge TMR that include the TMR number 1 and 3 and TMR 2 and 4. And here shows the TMR 2 and 4 and TMR 1 and 3. So the sensitivity shows the using a biasing voltage of the around 1 volt. So the output voltage peak to peak was around 325 microtesla, with a sensitivity of the 113 volt over Tesla. So this was the sensitivity, and the noise that you can see that it is very less than nanovolt over square root hertz. So in addition to tunneling magnetoresistive sensors, we have done a collaboration with University of Kiel and Fraunhofer in Germany to work on the magnetoelectric sensors. So magnetoelectric effect is the coupling between the electric and magnetic fields. So in fact, the mechanical coupling between the magnetorestrictive, which shows as a MS in this figure here, so magnetorestrictive materials, and piezoelectric materials. So piezoelectric materials with the PE and magnetostrictive here. So that this actually gives us a equation which which is the effect of the, we have a mechanical over magnetic and then electrical over mechanical. So which at the end what we have an electric over magnetic. So the output will be the electric over magnetics that we will have. So this is the magnetoelectric sensors. The benefit of such sensors, as you can see, this is the structure. We use the aluminum nitride for the piezoelectric layer and iron cobalt SiB we used for the magnetostrictive layer. So the benefit for such sensors are, the first of all, they are passive sensors. They offer a very high sensitivity with the small dimensions at the room temperature, and they are extremely low power. So this is the magnetoelectric concept that, as you can see here, the dimensions also exist. So simulations using the finite element method using COMSOL. So the total displacement or magnetostrictions, piezoelectricity. So we have done all of them for the detection of the few picotesla that require for the in this work, as you can see here, so the sensors was placed inside a Helmholtz coil for the magnetizations, as well as for the cancelling the noises, and we could achieve DC sensitivity with the resonance enhancement, as you can see here in the two frequency, in the three frequency F1, F2, and F3 that's required for the magnetomyography applications. And also the AC sensitivity, as you can see, you can by increasing the AC magnetic field, we could have a linear response, as you can see in these figures. Here we can see the fabricated sensors. So here, packaged and assembled magnetoelectric chip on a test board. The figure below here shows the magnetoelectric sensor device with the number one shows the cantilever. Number two shows the edge grooves with the three is a bond frame, and here we can see the wire connecting to the bond pads. The experimental setup shows here again. We can see that we have used the magnetic shield tube here with an active geomagnetic field cancellation box, as you can see. And compared to the other technologies like SQUID, optical pumped magnetometers, OPM, and giant magnetoresistors, so this work, magnetoelectric sensors, offer 175 picotesla sensitivity, which is at room temperature compared to the other technologies, and it offers a much higher sensitivity compared to the giant magnetoresistors. In addition to magnetomyography, the other applications that can be considered for magnetic sensors based on the tunneling magnetoresistors are wireless eye gesture control. In this work, we have embedded the magnets into a contact lens and we used the magnetic sensors in a wearable eyeglasses frame. In that case, we could detect the eye movement using the sensors that can integrated into the glass frames, and based on classifications, we could use the signals for the movement for the different applications. Here shows a small video that how these sensors can be exploited for the different type of technologies. For example, for an eye gesture based game or control a wheelchair and other applications. In this work, we have used the tunneling magnetoresistive sensors again for the different applications with the different structure. So this work, since the sensitivity is not like the magnetomyography, we have used different kind of TMR sensors with the less number of the magnetic tunnel junction, but the structure at the end, the structure is we adopted the structure to sensors that fits, and we could detect the movement of eye in a different in the different directions using this system. So here the figure here shows the electronics for the readout, and at the end the output signals we could see at the graphic user interface. We have also used the different type of TMR sensors for embedding the sensors on an eyelid magnet and using the eyeglasses, which equipped with the miniaturized electronics. So we used such sensing system miniaturized for the control of the eyelid. So using this, we can indeed use this technology for different type of the applications like gaming, or like for the wheelchair commands, and so on. So this technology, in fact, for example, here we show that it can be used for gaming or for wheelchair control. Other application for magnetic sensors, it include lab-on-chip point-of-care diagnostics. In this work, we have shown a fully CMOS micronuclear magnetic resonance. So the signal was generated by a transceiver pulse which send certain pulses to excite the nucleus, and then using the relaxation technique we could read the T2, which actually refocused echoes from the atoms, and here shows the integrated chips, which includes a very large coil sensor, so sensing coil, and the chip includes the transceiver for NMR, and also we had a Hall CMOS sensors with the readout circuitry for the monitoring the magnetic field into a coil. So as you can see, the whole systems it was a handheld and portable. So the figure here shows the whole CMOS platform. The different blocks that have been included in this work was including the micro NMR transmitter here. So we had a receiver, and as mentioned, we used the vertical based Hall sensors for the monitoring the magnetic field inside our magnet, which generated around 500 millitesla, half a Tesla magnetic field, and based on that we could calibrate and we could use it for the thermal compensations. So here we could see the samples. It is around the 2.5 microliter on the coils. The last example of using magnetic sensors for the medical applications, here we have used magnetic sensors for detection of the malaria hemozoin. So we used this work since last year, and we noticed that with other colleagues from Uganda, we noticed that inside the red blood cell, and in case of the infected red blood cells, which is the parasites, so we will have a small paramagnetic particles. Using the very high sensitive sensors, such as the magnetoresistive sensors, so in our case, we have used the TMR, so we could detect the very small paramagnetic particles inside the parasites. So this work will make a device that non-invasively can detect the parasites within the infected blood cells. So, and this is actually will change the very conventional technique using a bulky devices. In this regard, the blood samples require to be magnetized using a magnet up to 1 Tesla, and then using the TMR sensors, we could read the number of hemozoin inside the infected red blood cells. So using the TMR sensors, indeed we could detect the number of the hemozoins inside the Hallbach array that could generate 1 Tesla magnet. So in this regard, as you can see, the different actually signals was detected, which was included the help of our colleagues from Uganda and from medical school in University of Glasgow. The TMR sensors was configured in a full bridge, Wheatstone bridge, and then we have amplified using a transimpedance amplifier and with low pass filters, and then digitized to show using a portable user interface. The work was recently presented at ESSCIRC. Here shows the experimental setup and the our Hallbach array that generated the 1 Tesla with the user interface and the PCB base readout circuit. So the cartridge and the hemozoin samples, you can see the blood here, which how we could actually bag them and put inside the Hallbach array, and you can see the linearity of the number of hemozoin particles versus magnetic field in this graph. For further miniaturization, our colleagues at University of Stuttgart we developed a readout chip that manufactured in 180 nanometers SOI CMOS technology, and we could integrate it with the TMR sensors to achieve a thermal noise floor of the around 5 nanovolt over square root hertz, while consuming 38 milliwatts. So this work is presented next week in ESSCIRC ESSDERC conference, and the TMR and readout circuits provide a very low magnetic field noise floor of the around 120 picotesla over square hertz. And the microsystem, the whole, also features a 10-bit on-chip current DAC that allows compensating for the large process variation in the TMR-based resistance value. This slide brings us to the conclusion and future direction of magnetic sensors for medical applications. We could see that magnetic sensors has a potential to be used in a different wearable and implantable applications for medical deployment. So the four directions that I can see the future. The first is a human-machine interface with the wearable implantable magnetic sensors. The second is to empowering the neuromorphic computing using the nanoscale oscillators. We also saw that in updating and improving the stability of the magnetic based sensors that can revolutionize the portable medical diagnostics, and at the end the flexible magnetoelectronics for electronic skin compasses and electronic haptic sensing, so that will be revolutionize the future of the such electronic skin technology. So at the end, I would like to thank my group members, all of my group members, Microelectronics Lab at the University of Glasgow, and thanks the founders of my research who generously supported our research to achieve our ambitious goals. As papers to see this year in ESSDERC conference, I would like to invite you to our papers in collaboration with University of Stuttgart, which will be Thursday, 16 September. Thank you very much, everyone.